Let's have you guys try. I'm talented and gifted.
I'm not talented.
Let's have you guys try this one. And you don't need to do it on a whiteboard. I would do it in your notes. Write it into your notes. So again, basically, the electric field is easy. You just say QVB equals EQ, right? The Q's cancel, and it's very simple to calculate E, right? But then we got to figure out the direction of it, right? So let's all figure out the magnitude, and then notice I give you the mass. Do we need the mass for this? Not as much, right? Has everybody gotten 1524, basically? Yeah? So the math is really pretty simple. Okay? The math is pretty simple. It's just, if the Q's cancel, then E is just V times V, right? So in this case, it's 1.27 times 10 to the fifth, right? Meters per second times 0.0120 Tesla. So it's got 3 sig figs, right? The answer I get is 1524. Which is 1520 newtons per coulomb with sig figs, right? Now let's do the direction, okay? Let's look at the direction. And I hope you understand that at the very least, it's going to be to the right or the left, okay? Because it has to be perpendicular to the velocity and it has to be perpendicular to the magnetic field, right? So the only thing that's perpendicular to both is the right and left direction, okay? So the electron is going this way. It's a negative charge, right? So which way is the magnetic force? Well, index finger this way, magnetic field into the page, yes? It's to the right, only it's negative to the right. So it's to the left, okay? So the magnetic force is to the left. Nope. X is into the page because it's the fletchings of the arrow. Yeah? All right. Guys, we're in the middle of an exciting explanation here. Okay? So the magnetic force is that way again. Velocity this way, magnetic field into the page. It's to the right, only it's negative to the right, so it's left. Yeah? Okay? Which way should we exert a force to make it go straight? To the right. So the electric force should be this way, right? Okay. Now, which way does the electric field need to be to exert a force to the right on that guy? It needs to be to the left. Okay, the electric field needs to be this way, right? Because remember that an electric field that exerts a force to the left on a positive charge exerts a force to the right on a negative charge. You made 2 mistakes, you know, right? And then you're all set. Now, if you think about that, if it's a positive charge, if you take out the charge, you're going to always make 2 mistakes, aren't you? If you forgot that it was an electron, you would make automatically 2 mistakes. The first is that you'd say the magnetic force was this way, and then the second would be right. Okay? So you're always going to get it right because Q cancels out, doesn't it? So its positive or negativeness also cancels out. So if the electron is too confusing for you, with all of its not to the right, to the left kind of thing, just do it for a positive charge and understand that the electric field for both charges will be the same, the direction of it. That's weird, isn't that weird? That is very weird, but it has to be the case, right? Because the charge cancels out.
So what you're saying though is like, if you were to fire positive and negatively charged,
They go straight.
into an electric field with an electric field already in there, they just go straight.
Electric field and a magnetic field cross like this, they would go straight.
So they cancel out.
Yeah.
Does it affect anything or the actual particles themselves?
Only the charge. The question is it affected by anything else? It's only affected by the charge of the particle, or the velocity of the particle, right?
So, but like once they enter if you just fire them in there, once they enter that cross electromagnetic
Yeah.
field, they're not going to do anything.
If they have that particular velocity, they're going to go straight. Yeah?
So it comes down to that velocity.
Yeah. Isn't that cool? Is Dinadu asleep?
Raffo! I hate you, Jordan. What is your problem?
You can shoot him anyway.
I wasn't going to light a firecracker. I was just gonna
Dang it.
biscuit. Okay, so the question was if you fired any particle straight down into this field, regardless of whether it's +1, +2, -1, -2, it's going to go straight. Isn't that interesting? Okay, but it has to have exactly that velocity. If it's got less or more, then it's not going to go straight. So you can use a crossed field like this as a velocity selector. If the particle is charged, you can cross the fields and actually make a velocity selector. And in fact, that's what we do. We actually use this for, voila. Okay, this is, okay, this thing is a mass spectrometer. Okay, so this picture here, this thing here is a velocity selector. Okay, this is just a magnetic field, and particles that come in here that are heavy go around in a wide circle. Particles that are lighter have a less wide circle. Okay, so here is just a magnetic field, and so that's our normal sort of going in a circle sort of stuff. But this is a velocity selector there, right? And so if you look, there are actually two slits on this thing. I need to point. I must point. I must have a ruler. Here it is. Okay. So here, I know. Where is it? I've got a big laser. So here's a little slit here. This is a source of charged particles. Basically what you do is you take your particles, like you take iron, right? And you basically hit it with like an arc welding torch. You make a plasma out of it. You totally ionize it, right? You also, by the way, a plasma is particles going really, really fast because they're hot, yes? Okay? So you make a gas, a glowing gas of iron. Some of the glowing gas you allow to escape through this slit. Now, the ones that are going at this particular velocity such that they go straight actually make it through, and all other particles are absorbed or sucked off into the vacuum system or something like that. Okay? So only particles going with a particular velocity are going to go through that region right there. Okay? And then, so let's draw a little picture of that, right? Okay? So in this region, we've got magnetic field out of the page, right? And we've got a little slit like this and a slit like this, right? And we've got some source like that. And so these particles, the ones that go straight, we can say this for sure. We can say that QVB equals EQ, Q cancels, and V is E over B. Isn't that cool? And we can, by the way, determine what the magnetic field is, what the electric field is. These are things that we can just make this thing, right? So I could make something that will only let through something going 1 × 10⁵ meters per second. Isn't that cool? Right? Okay, it has to be charged. If it's a neutron, it can it'll go straight anyway, right? It's not curved by magnetic fields or electric fields, right? Okay. Now, once it gets into this region, right, and this can be far, far away in a galaxy far, far away or something like that, right? We've got a little slit like this, and we've got a magnetic field, a different magnetic field. So I'll call this B prime, like Optimus, right? Right? Okay. So once it gets into this region, into the second region, it's just going to do a little curve like this. Like that. That's a pretty nice curve, right? Okay. So it's going to shoot around here and go, and it's going to hit someplace here. Now, can't we easily measure this radius of curvature? Yeah? Can't we easily measure that? Here's how you measure it.